So we're now going to start talking about how Java Parallel Streams uses the common fork join pool in order to actually implement parallel processing. And this discussion is also described at some length in the article at the bottom of the page. Looks like I'll have to fix the link again, but that'll be fixed in the slides that I'll put out later. So if you get the PDF version, it'll have the right link. For some reason, I think I mentioned IBM keeps changing their links, which is annoying, but we'll solve that problem in the final version. So if you recall the different phases that are used for parallel streams, the split iterator phase, the split phase partitions the data source up into chunks, and then those chunks are handed off to the common fork join pool to be processed in parallel. What is a fork join pool? We've outlined this before, but just to kind of recap and revisit this topic, a fork join pool is a framework that provides a high-performance, fine-grained task execution model for Java data parallelism. And what it is used for, you can use it in its own right. And if you take my course that's on concurrent object-oriented programming, we'll actually talk about this. But in the context of this course, we're not really going to talk a whole lot about the common fork join pool for fork join purposes. We're going to talk about it primarily from the point of view of how is it applied by Java's functional parallel programming frameworks, things like parallel streams, completable futures, and then later things like reactive streams. I'll spend a little time talking about the framework as the framework just because it's interesting, but the bulk of the discussion of how to program fork join pools appears in my sister class to this one. Fork join pool is the main interface to the fork join pool. The fork join pool class is the main interface to the fork join framework, and it implements the executor service interface. Again, this is a topic that we won't spend a whole lot of time on in this course, but in other contexts, we'll talk a lot about the executor framework. And the executor framework is a very powerful framework that's used for primarily to have various types of thread pools. And you can see here that there's several different types of pools. There's a thread pool executor and a scheduled thread pool executor. And then there's something that's called the fork join pool. And that's, of course, what we're focusing on here. The fork join pool itself is an object that's used to execute so-called fork join tasks. And a fork join task is an object that associates a chunk of data, which is a partitioned piece of the overall data source, together with some computation on that data, and it's done to enable fine-grained parallelism. So it's very lightweight, as we'll see here in a second. So you can think of a fork join task as basically a very lightweight thread. And I'll compare and contrast fork join tasks and threads here in a second, but that's kind of the way to think about it. It's like a unit of computation that doesn't have all the state and behavior of a full-blown thread. So in particular, a regular Java thread, which I show here all pumped up and injected with steroids, is going to have its own runtime stack. It's going to have its own registers. It's going to have its own thread local storage. It's going to interact with the operating system kernel in order to be able to be scheduled and run and suspended and resumed and so on. And a fork join task is kind of like the scrawny little brother or sibling of the big honking thread, which is much lighter weight. As a consequence of being much lighter weight and not having its own stack and not having its own registers and not having its own thread local storage and so on and so forth, you could actually have a very large number of fork join tasks that are then multiplexed or run on top of a much smaller number of Java threads, which are called worker threads, in the context of something called a fork join pool. So the fork join tasks, you could have, literally thousands or tens of thousands or hundreds of thousands of fork join tasks that would then be multiplexed atop a very small number, typically the number of cores on your processor that the JVM knows about, your execution environment. You could have as many fork join tasks pretty much as you want, and then they're going to be run atop a much, much smaller number of actual Java threads. So in essence, this allows us to have a user-friendly functional programming facade, and that's what parallel streams provide. So it's basically a nice, easier to program, more functional, more composable, et cetera, et cetera, et cetera, facade that wraps around the behavior of fork join pool. And that's fantastic. That's exactly what you want. Facade is basically just a kind of a wrapper around something complicated to give you a simpler interface. It is possible, of course, to program with the fork join API directly if you want to, although it's painful, and in many cases, it doesn't actually give you a win in terms of performance. And I'll show you that a little bit later. We'll definitely talk a lot about that when we talk about the fork join pool in my concurrent object-oriented programming class. But as a general rule of thumb, it's not worth programming with the fork join pool. You can instead use the encapsulation of that in the form of parallel streams, and you get pretty much the same performance with much, much less complexity of programming. And I always think about the famous scene from Lord of the Rings where Saruman tells Gandalf, "I gave you the chance to join me willingly, but you have elected the way of pain." And that's kind of the way I feel about fork join task. You're better off to be using parallel streams than programming to it directly. If you want to see an example of something that uses fork join task, there's a kind of a fun folder called searchwithforkjoin.java, which is in my, or it's a file rather, searchwithforkjoin.java in my Stream Gangs implementation, and it shows how you can implement the behavior of the search Stream Gang program using fork join tasks. Again, you'll see it's just extra work and doesn't really give you any speed up, which is the part that's kind of interesting. Fork join pool, if you use it at all, is probably best used for programs that don't quite match well with the parallel streams model. The parallel streams model, as we've seen, is really based on kind of divide and conquer, using splitterators to take a source of input and chop them up into roughly even-sized chunks, and then have those chunks mapped down onto the underlying processor cores. Not everything fits into that model. And here's a simple example that you can get from this link that demonstrates when you might want to use a fork join pool instead of using parallel streams. So this particular program counts the occurrence of a word in a recursively structured folder hierarchy. So we've got a bunch of folders that contain subfolders and documents and so on. And this piece of code here called compute is going to go through the folders and look to see where a certain word occurs or a phrase or whatever. And you can just read more about this article here. And then I have some examples of this in my repository on my GitHub account. So the way this works is we start out by making ourselves a linked list of so-called recursive tasks. And a recursive task is basically a subclass of fork join task that has a method called compute defined on it that does the heavy lifting for computation. So we then go ahead and we iterate through all the subfolders in our folder. And for every subfolder, we're going to make a new object called folder search task. So we make a new folder search task with the word we're looking for, which is called mword. And then we are going to add that task to the forks list. And then we're going to go ahead and fork that task. So notice what we do is we make ourselves a new folder search task object. We add that to the list that we're keeping called forks, and then we go ahead and fork the task. And the fork basically arranges to process that subtask in parallel in the common fork join pool. And then down here, we go through all the documents that we have within a given folder. And what we do is we make a new doc search task that is going to search a given document for a word. And then we go ahead and we add that to the task list. And then we fork that task. So that then goes off and gets scheduled to run in parallel. And then after we've kicked everything off in motion, and this will all run recursively as well, if you have subfolders, then we end up going through a loop for each of the tasks that's in the forks list. So for each recursive task, we're going to join with that particular task, and then we're going to increment this count that we're accumulating. And what join does is join has this cool semantics that basically says, don't block the caller, go off and help to run the processing that's taking place in parallel in the background in all these different fork join threads that are running around in the common fork join pool. And as those things complete, then the count gets incremented. And the final thing we do is we return the count. So this particular approach, you could actually also do this with parallel streams, but in this particular case, we're just going through the folders and the documents within a folder and doing this processing. So it's fairly clean, fairly neat, and doesn't really lend itself particularly to the parallel streams model, although you could write it that way. But this is a nice example of using the common fork join pool. All parallel streams in a process share the same common fork join pool. So there's only one common fork join pool per process. So you can basically think of this as sort of a logical singleton. It's not actually implemented using the singleton pattern, but it's logically singleton in the sense that there's only one of these things. Why do we do this? We do this because it helps to optimize resource utilization by knowing what cores are being used globally within a process. So I always think of, whenever I think of optimization, I think of Professor X with his cerebro chamber, looking out at the whole world with his big brain to see what's going on. And so we're basically using this so that we can steal the threads appropriately, they're in the right way in this big pool of computations that are running all the parallel streams within a process. This kind of global versus local resource management trade-off is very common in lots of places. For example, it's also used with Java's heap. So as you're probably familiar, Java has a global heap, and all the memory that's allocated in the process by default comes out of the global heap. You could also manage your own sort of free list, but it's not recommended for various reasons. So essentially, this same concept of having a global resource that's used to optimize performance by having a global perspective is not uncommon in other parts of Java and other places as well. There are deliberately very few knobs to control the common fork join pool, or actually any fork join pool for that matter, not just the common fork join pool. And this is intentional. If you want to learn why this is intentional, why they try to keep things fairly simple, you should watch this nice video by my good friend and colleague, Doug Lee, who wrote Fork Join Pool and many other concurrency frameworks and mechanisms in Java and other technologies too, for that matter. And he has this nice video that talks about the design rationale behind concurrent library components in Java, and he explains why they did it this way, because they found that the other approaches that were in other frameworks were too complicated. In particular, the thread pool executor, which is another implementation of the executor service interface, has a much more complicated API, but it's not always clear that that's a win. So the fork join pool, very simple. The thread pool executor, very complicated, and yet in many cases, fork join pool works just as well, if not better, in most circumstances, because it's able to keep the processor cores busier than other mechanisms you might get out of the box or you could implement yourself. There are a few things you can control, however, with respect to the fork join pool, and we'll talk a bit more about them, the common fork join pool, that is. You can set the desired number of threads in a very particular way, and you can also control dynamically by using something called a managed blocker. And so we'll talk about that here in just a second. So that's the end of the overview of the common fork join pool and how it's applied with parallel streams. We will look in more detail here in the next couple lessons to see a deeper understanding of how these things work.